Okay, AP Chemistry kids, welcome back to part two of how to do pH calculations with a weak acid, strong base titration titration curve. And I just kind of want to get you back to where we were. What we did is we calculated the pH going along this side of the acid side of the pH of the titration curve, and we're building our titration curve. I had asked you guys to calculate the pH of a titration curve with using 40 mils, and you came up with a 5.35. So looking at our curve, it's kind of it's starting out a little bit higher than our strong acid. It's at a pH starting at 4.14. We're at 5.34. So now we want to look at where we are when we add 50 milliliters of a 0.1 molar NaOH to our 50 milliliters of 0.1 molar acetic acid. Okay, hopefully that's ringing some bells for you right now. You should say, hey, wouldn't that be the same amount of stuff? And yes, we are. We're talking about the same amount of stuff. Our major species are still the same. But when we look at the stoichiometry piece of this, since we are talking about then 5 millimoles of OH and 5 millimoles of acetic acid, then we allow this reaction to happen, like literally think in your mind, allowing the OH to bump into this. We would completely have no limiting reactant. They're at a perfect stoichiometric point. This is called the equivalence point, okay? And you would have no more OH, you would have no more acetic acid. It's been all converted to the acetate ion, and you formed 5 moles of it. So now you're at the equivalence point. But what's interesting is that now, when I look at this, there's a new reaction in town. And the new reaction is because this acetate ion is a strong conjugate base. Strong conjugate bases want to hydrolyze with water. Yep, you said it. They want to react with water, where this will be the base, this will be the Bronsted-Lowry acid that's going to donate a proton to that acetate ion to make acetic acid and OH. Okay? So this is a new reaction that you have to write down. It's a new equilibrium reaction. And what's going to happen is you're going to calculate, well, I have 5 millimoles of my acetic acid. My total volume now is 100 because I originally had 50 mils of acid and I added 50 mils of base. So my total solution now is 100 mils. I haven't allowed this association, this reaction, this hydrolysis to happen yet. So none of this has been made. But when I do, okay, I can write this as the equilibrium line. The equilibrium line will be 0.05 minus x, and then x times x. So the other thing, hopefully you're checking out here, is that we are now in a basic solution because we've got hydroxide. So you got to convert that Ka to a Kw. The Ka to a Kb through the Kw equation. So the Kb is 5.6 times 10 to the negative 5. How did I get that? Well, I put 1.8 times 10 to the negative 5 here. I know my Kw is 1 times 10 to the negative 14. So my Kb is 5.6 times 10 to the negative 10. I know I misspoke earlier. This is the correct Kb. And the Kb expression is written right here. Kb then would be the acetic acid times the hydroxide over the conjugate base of CH3COO minus. So when I do this work, now, okay, I'm just plugging in what I know. This equilibrium line right here just got plugged into my equilibrium expression, and I can ignore the minus x because it's so small. That becomes x, which becomes then the hydroxide, is 5.3 times 10 to the negative 6. If I take the POH of that, I get, where is that? Somewhere in here. I get 5.28. And then the pH would be 14 minus the 5.28. And I get a pH of 8.72. Notice that this pH is above 7. This is true for all weak acids titrated with a strong base. They will have a pH greater than 7. And the reason is because of the hydrolysis that goes on. And if you think about that hydrolysis of a salt, this will all kind of make sense. If you remember that from chapter 14, this hydrolysis reaction makes a base. So of course the pH is going to be higher than 7 at the equivalence point. Okay? So that's just something to consider. All right. Well, what happens then if we were to add 60 mils of base? Okay. Well, now my major species are still, I have acid, I have base, I have sodium ions, I have hydroxide ions. I'm going to go through the stoichiometry piece of this. I'm adding 6 millimoles of hydroxide. You can see where I got that 6 millimoles from. 60 times 0.1 molar, 6 millimoles. I originally have still my 50 milliliters of 0.1 molar acid. So now the limiting reactant is the acid. That's going to be all consumed, and we're going to have excess hydroxide. You still want to write out this stoichiometry piece because you also have to know how much of the conjugate base you form when you do this titration. And in this case, it's 5 millimoles. Okay, where did that 5 millimoles come from? Right here, because you used up all of this H from the acid was reacted. And so you have 5 millimoles of the acid left over. Okay, and of course the hydroxide is the excess reactant. Now, major species is the acetate ion, the sodium ion, the hydroxide ion, and the water. And you should be saying to yourself, who's controlling the pH? Well, hopefully you recognize that the pH is controlled by the hydroxide. There is excess hydroxide. Sure, this acetate ion is going to also react with water to make a little bit more hydroxide, but guess what? That is negligible compared to the amount of hydroxide that you have in excess. So that makes the calculation a lot easier. So the amount of hydroxide that is produced by the hydrolysis of the acetate ion is negligible, and you can calculate the amount of hydroxide that's in solution by taking the amount of excess in millimoles that you had over the total amount in solution. 50 mils plus 60 mils makes 110 mils. And so now the hydroxide ion concentration is 9.1 times 10 to the negative 3. So when you take a POH of that, you get a POH of 2.04, and you would get then a pH of 11.96. Okay, so this part of the calculation gets really easy, but it's important that you understand the chemistry that's going on, that the pH is being controlled by the hydroxide in that part of the titration. So if we were to look at what because I didn't do this in the last slide, so I'm going to kind of just show you where we are here in our titration curve. So remember, we started out a little bit high like that, and you're going to see then the equivalence point. Now we're kind of at the point up here again. So the equivalence point that we had her here in this slide, remember we said the pH was 8.72 at the equivalence point. So that's probably somewhere right there about here. So we'd say that our 7 mark would maybe be somewhere about there, just a little bit lower. And we're building on this part right up here of the titration curve. All right, finally, and I believe this is the last one that we're going to do, is what if we add 75 mils? Okay, now hopefully this is just an exercise for you guys that you would recognize that we're still going to have excess hydroxide. The procedure is still the same. Hydroxide is still going to be controlling the pH. What I'd like for you guys to do right now is to pause. I'd like for you to do this math, fill this in, make sure that you get what I got. So pause and do your math, do your work. When you got it, come back to me. We'll see if we're right. So go ahead, pause. Okay, hopefully you got it now, and you saw that the hydroxide ion concentration, I didn't really calculate what that was at, but you should have a pH of 12.30. So the other thing that I find interesting when you're drawing your curve, okay, and this is for a weak acid, you kind of have this area in here, and then, and really, let me erase that because it really shouldn't be this steep. It's one of those things that they're not quite as steep as you think like they are in a strong acid, strong base. But you got this part of the curve, okay? And then what happens is it kind of tails off there a little bit. And so you're really in that excess area here, that the pH isn't changing that much because you're in high pH, you're in high hydroxide ion concentration as far as your excess, okay? So those two videos, part 1 and part 2, explain how you calculate the pH of a weak acid with a strong base titration system. I hope that helps, and I wish you luck. Good luck.